experience. We've only been in the UK for 3 years, but we can lean on the experience of all of our European partners from the Nordic sector, Scandinavia, the marine sector, and the world's leading HVAC brands who have our technology within their warranty documents because they don't want to have chemicals within their products. The recognition of what we do. We talk a lot in the UK about following the Danish guides for our district heating systems. And over the last few years, we've adopted their principles for low temperatures, wide deltas, and pump control, metering, efficiencies. But the one thing that we've skipped over is what they say about avoiding the use of chemicals. So the Danish network guide says we should avoid the use of chemicals. And the reason for that is if you have a district heating system which leaks into the ground, you're putting chemicals straight into the water table. The Nordic Innovation Centre report in 2004, that long ago we had 500 systems in operation using our products in Norway in district heating networks. VDI 2035 is a German standard, and that is all about chemical-free water treatment, and you'll see that mentioned in a lot of the big brands, manufacturers' warranty requirements. So world-leading brands have got it in there. VDI, you should follow VDI for your warranty purposes. And in the Swiss and Austrian norms, all about chemical-free. And we've had the efficiency of our products tested by most respected Dr. Philip Mung from Midland Corrosion, because the obstacles we were getting when we first started in the UK were people saying, well, it's okay on European water, but our water's different. So just to prove the doubters wrong, we had it tested in UK laboratories. And then more recently, what I'm really pleased about is CIBSE, the Chartered Institute of Building Service Engineers, have recognised our methods in 2 of their district heating guides. In the Heat Network Code of Practice, VDI is now accepted. And in the Heat Network Design Guide, there's a statement in there which says it's the best method for large volume networks or for networks that operate on low and intermittent flow, which pretty much covers everything we do in district heating. We've got multiple case studies in a new build environment and retrofit, but more and more now it's clients who are doing environmentally friendly products who want to start avoiding chemicals. So the major networks that we've been involved in is Bun Hill. Bun Hill was the world's first project to take heat off the London Underground and heat up homes in Islington and schools and a leisure centre. Renewable energy product, there's a heat pump which sits on top of a disused underground station, taking heat from 30-35 degrees up to 70 for district heating. And it made no sense to have a renewable project but then fill it full of chemicals. Barking Riverside is a scheme in London which is going to be 16,000 homes. Started its life as a chemical system, but for complications of phasing, they've now moved to chemical free, which makes the phasing a lot easier when you're not using chemicals. Stoke City Network and Swaffham Prior, a project we're really pleased about, which I'm going to talk about more. And in Viking Network, hundreds of smaller district networks we're on. And then developers who are concerned about the environment and are moving to heat pump technology. So it makes no sense on one hand to say, I'm putting an environmentally friendly system in, I'm going to use heat pumps, but then I'm going to fill it full of harmful chemicals. So if you've got renewable technology, look at other things as well to look at the carbon emissions. So Swaffham Prior, well, the UK's first project was 100% renewable energy. It's using ground source heat pumps, air source heat pumps, and a solar PV field to generate the electricity for the energy centre. It's our largest district network to date, 450,000 litres of water, all done without using 1 litre of chemicals. Now, if that was a chemical system, that would have needed 9,000 litres of chemicals to treat that system for commissioning and cleaning and biocides, which equates to 450 20-litre drums to give you an idea of how much it would be. And of that, 50% of that would have gone down the drain because you'd have used it for your cleaning, your process, dumped it, and then refilled again. So we have done it without using 1 litre of chemicals. The client and the pre-commissioning contractor were new to our technology, so a bit sceptical about would it work. But working together with them, we come up with a plan, a pre-commissioning plan, to make sure that they got through the process and it was painless. So the energy centre was cleaned by filtration, and the district network by ice pigging. I don't know if anyone knows about ice pigging, but it's a bit like a slush puppy, which is pushed through the pipe. And as it pushes through the pipes, it cleans the debris, and the ice just pushes the debris out to the other end of the network. So the process of using chemical-free for a pre-commissioned contractor is no different to what they do with chemicals, apart from the fact they don't use chemicals. So their cleaning medium is bacteria-free, demineralized water. Instead of using chemicals and biocides to do that cleaning process, they use bacteria-free, demineralized water, and that's finished off using our devices using electrochemistry, which absorbs the oxygen, uses the oxygen, and controls the pH and conductivity. So the process was filled with the bacteria-free demineralized water. Side stream filtration unit was used to get out the system debris from the pipeworks, and the system was filtered, but without putting anything to drain, just capturing the filter, the debris in filters. And then the energy centre was circulated through the primary and secondary pipework. Everything was tested, and then VDI, what VDI says is that 10 to 12 weeks after commissioning, you should check to make sure everything's stable, which is different to the UK, which is like a 7-day test. But it's 10 to 12 weeks, it's making sure everything's okay. So the process, water was sampled at appropriate intervals. Working with sewers, the underground pipe was ice pigged. The ice pig was pushed out using demineralized water. So they inject the ice into the pipe and they push it out with demineralized water. But their demin water wasn't quite at the levels we wanted it to be. And that fresh water is going to be full of oxygen. And oxygen is the biggest cause of corrosion, so we want to get that out. So the solution was to connect some of our mobile units, which I'll show you in a minute, to the underground network. So once it's been ice pigged, once it's been filled with demin water, which is lower pH than we want it to be, but it's full of oxygen, connect our magnesium anode technology to that. That consumes the oxygen, and in doing so, it pushes up the pH to get exactly where we want it to be. Only a one-time fill. So as well as avoiding the use of chemicals, we've only used 450,000 litres of water. Normally you'd be using double the amount of water at least if you're doing a chemical flush and clean. So we're not only avoiding chemicals, we're also saving on that water. This is our mobile unit, so this is what was used to connect to the ice pigging. After the ice pigging, we connect our units to the system. These are full of magnesium anode rods. The magnesium anode consumes the oxygen and releases magnesium hydroxide to push the pH up and control the conductivity. Because we want to control the three things with chemical-free: the pH, oxygen, and conductivity, which is all done by the electrochemistry. That's the finished energy centre. Swaffham Prior, if you look it up, you'll see all about it. It's a very exciting project. That's our two large electrochemistry units, maintaining that water going forward. So we filled it with the demin water, bacteria-free, and now going forward it being maintained with our devices. And this is done by our chemistry graduate. Most of our clients, we have that oh my God moment, it really works. So the skeptics, once they've used it and they see the results, and their oxygen and magnesium, using the oxygen from the system to produce the magnesium hydroxide for the system is all we need to do. So it's very simple, school level chemistry. I'm not a chemist, I'm a gas engineer by trade. It's a simple solution for everybody to adopt. And this is why we're being taken up with very big district heating networks in the UK. Thank you.
Hi, good morning everyone. I hope you can all hear me well. I'm Mark Nichols from Kingspan Technical Installation. I'm the National Business Development Manager for Kingspan. I'm here to talk to you about secondary pipe installation networks and a new calculator tool we've launched, which should help with CP1 calculations to the new 2020 edition. So to start with, we'll touch briefly on CP1. I'm sure everyone here is familiar with it. If you're involved in secondary installation networks, you've probably looked at it, gone to the sections that are most relevant, looked at the outputs that you need to produce evidence for. But I think it's worth touching upon, within the document, it highlights a couple of points. That when you're looking at the installation, you shouldn't just be looking at pure heat loss. You should be looking at the cost benefits of additional installation and the impact on CO2 emissions, and then actually using your project conditions which generate it. You shouldn't be using standard assumed conditions that are in, say, a BS 5422, a CIBSE Guide C. You should be using your actual project, what your conditions are, and using that to calculate all your losses. So to start with what CP1 says about thermal insulation, you've probably seen this table before, which is a great improvement on the previous edition of CP1. So we've got both phenolic foam and mineral wool considered within this table. Obviously, as Kingspan, we manufacture Cooltherm, which is a phenolic insulation. So here it's got both phenolic and mineral wool, both at 50mm thickness and 60mm on the greater sizes. Obviously, those two different materials have got a performance difference to them. So when you're doing CP1 calculations, in some ways this becomes a distraction, because what you actually have to do is the 3.9.8 calculation. So you need to take the annual heat loss from the plate heat exchanger to the HIU and divide that by the number of dwellings. So this is really the key part for thermal insulation within CP1 for the secondary network. And really, the calculator that we've only just launched looks specifically at this, the annual heat loss from your heating system, and really helps with the CP1 side while also considering that carbon element and considering the cost element. So I was hoping to give you a live demonstration, but we don't have internet up here, but we do have internet over on the stand if you want to come get a demonstration. So essentially, if you've ever used the log store tool, the TCO tool, this probably looks fairly familiar. It's essentially been based on that. So essentially, we've got the tool here. At the top is where you enter your project conditions. So all the boxes that you can see are amendable. So you can change your flow temperatures down to as low as 25 degrees or as high as 95. Same for the return temperatures. The ambient temperatures, you can go down as low as -10 or up to plus 40 if you so wish. So you can actually calculate what you're looking at, because this isn't based on a lookup table looking at calculations that have been done in the past. There is a heat loss calculator behind this, which will dynamically calculate as you go. So whatever you change in the calculator will be shown in the results. We've got the operational hours, which are amendable. We've set in this example to 8760, which is 24/7 operation. We've got the energy price, so that's your price per kilowatt hour. In this example, it's set at 7 pence, but this value was taken about 18 months ago. So given the recent events in the world, I'm sure that's different for most people and most projects. Or depending on where you sit within the chain, if you're a generator, it might be less. If you're a customer buying the energy, it might be more. So it very much depends on where you sit and where your interest is. You've got a measurement there for the carbon intensity of your heat. So depending if you're using a gas CHP system, whether you're using an air source heat pump, you can modify that to reflect the system that you're actually using. We've got a variable lifespan, which you can change from 1 year up to 100 years, depending on the lifespan of the project you're looking at, or if you're working on district heating, the contract length that you might be working with. And then we also included the option for surface emissivity. Obviously, most insulation you see on heat networks tends to have that silver finish to it, but if you're putting it externally and putting some more cladding on it, that can change the surface emissivity, which sort of changes the heat loss by around 10%, an increase by going to a high emissivity finish from low. So it's really important to consider that when doing your heat loss calculations to CP1. So once you've done all that, you've got an area to put in your pipe sizes, your pipe lengths. So the calculator will calculate flow and return separately. So it's not taking a mean temperature, it's taking actual what your losses from the flow are, what your losses from the return are. It's going to assume that it's 50% flow, 50% return, but you can press an arrow and input those two lengths separately. And what the calculator is going to do is going to generate results to 3 different insulation standards. So you're going to have BS 5422, which is the base minimum within the UK. It's what everybody should be insulating to as a minimum. It's got the energy technology list, which was promoted by the Carbon Trust and BEIS as it was, and I forget which acronym they are now, but the Carbon Trust within them. And then it's also that CP1 table we just looked at, so 50mm thickness on all pipe sizes. If you're thinking, well, I don't actually want any thickness that matches those standards, you can input your own insulation thickness. You can go all the way up to 100mm thick if you want. So depending if you've got space constraints, you might be able to go thicker than 50mm. You might think I've only got space for 40, so what does that do? And you can change that pipe size by pipe size. So you might say, I've got space for 50 on that size, but not on that size due to that constraint. You can modify all that. So what's it going to show you? So first of all, it's going to give you a comparison graph on embodied carbon and operational carbon. So the embodied carbon is taken from our EPD, and within the calculator there's a embodied carbon per meter of insulation, so you can get your embodied carbon of the build-up you've selected. But it's also taking that carbon intensity figure for the heating system, and via the heat loss, it's turning that into your operational carbon from the heat lost over the lifespan. So you can use sliders to modify this up or down, which will then change all the graphs as you go. So essentially this lets you put into perspective what is the benefit for carbon for going to a higher insulation standard. In this example, I think on the custom thickness I put 75mm just as an example piece here. So the embodied carbon increases, you obviously have more insulation, but actually the increased thickness of insulation is greatly offset by the energy and heat loss saved. So you'll save a lot more carbon by going thicker than you would do by just staying to a thinner solution. Secondary, we've got the annual heat loss. So this might be useful for anyone doing those CP1 calculations. So this will calculate the annual heat loss of the system, give it you in those values there. And if you're doing a CP1 calculation, you can just divide that by the number of dwellings, and this will tell you whether you're at where you need to be, whether you need to look at going up in thickness. Do you have scope to go less than the thickness that you're looking at? Or usually encourage sticking as close to CP1 as you can, because chasing after that best practice target. And then the real question we got from people is, okay, what is the actual benefit of this? This usually came from contractors saying this is costing me 2-3 times the amount of a British standards system. That's what I've quoted on. What's the actual benefit? So we thought, okay, let's quantify this. So using the energy price that you've input, in this case it was 7 pence a kilowatt hour, by looking at the cost of the lost heat and actually what is the best system. So the capital costs are based upon the sales price of our insulation with supply chain margin. So you can actually see the capital cost of the installation of the system you're looking at. So you can see here that a CP1 system is about 3 times that of the BS5422, but actually the operational cost of the system over the 30 years is around £300,000 cheaper for going to CP1. So even though on the capex front it's more expensive, over the whole life of the project it's actually significantly cheaper. So there is a benefit even when you're not working on a district heating project to going to CP1 standards. And by looking at this at an early design stage and presenting this to the client, people can make an informed choice on what they want. They can say, okay, these are the implications. Yes, I know I'm paying more, but these are my benefits, which helps with that conversation further down the line. Further to that, we also have a number of return on investment graphs. So it will show you how long that additional installation will take to pay back versus the British standards. So in this example, which is based on a project in London, it was 5.7 years over a 30-year lifespan. And then we do the same in carbon as well. So how long does it take to repay that carbon budget versus the British standards? So based on all the methods we've done, it looks like it's always better to go thicker on carbon, on cost. You're sort of going up to, if you say looking at 75mm over 50mm, depending on your system, the payback period's around 30 years. So there is a cost question of, should you go that high on everything? Are there certain areas you can get a benefit from doing so? It really helps to put this into perspective and help, no matter where you're sat in the supply chain or the contract chain, whether you're doing sustainability, initial design, detailed design, contractor, it puts it all into perspective. So what this also then gives you is the detailed data. So this will tell you actually the exact flow and return heat losses on the system you specified, as well as all the other information about capital costs, everything that goes into making those tables. This will give you for each of the 3 standards or your custom installation. And finally, we can then wrap it up into a report which you can then generate and put in your project pack. So essentially it's there to make the lives of designers and everybody easier, help you pitch where you actually need to design, what thickness you're going to need at an early stage. And that's more or less it for me. We are doing demonstrations of the tool over on the Kingspan Log Store, over on K12. So if you'd like to see the tool in action, come over and I'll be happy to show it you. I'm there all day. Thank you.
Brilliant. So thanks very much indeed to Mark. A really interesting and timely piece of software. Many people are not aware that the latest GL Energy Assessment Guidance actually requires you to do a CP1 calculation within your energy strategy, and many will fail. If you go on to RIBA, Royal Institute of British Architects, I actually wrote an article recently talking about this fundamental issue of secondary network heat losses. So without further ado, I'll invite Mark Wettle from CPV to come up. Mark is going to talk about the latest innovations that they're producing in their buried heat network pipes. Over to Mark.
Thank you, Simon. Have we got any...
Just go to there. You can use that was easier, and you can use that or that. Whichever.
Thank you. I can read that. Good morning, ladies and gentlemen. I'm going to talk to you this morning just for a few minutes about innovative piping solutions for heat networks, and more specifically about the pre-insulating piping solutions that serve them. So I think we all understand the need for the UK's this drive towards net zero and decarbonisation, and importantly, the role that heat networks play in this. And when we consider that the UK's heat demand is currently probably only 2 to 3% of that is served by heat networks, and the target nearly 20%. Then clearly we've got a long way to go, and it's important that we consider how we can bring more sustainable solutions and importantly more cost-effective solutions to heat networks, and as I say specifically the pre-insulated piping solutions that serve them. So a little bit of history. CPV is a UK manufacturer, supplier of heat network distribution systems and the pre-insulated pipes. In fact, we've got over 70 years experience in polymer technologies. Going back to the 1950s, we were very much in developing polymer technologies for chemical process, chemical drainage applications. And then in the 1980s, we moved into pre-insulated pipe work, predominantly carbon, steel and copper in those days. And then beyond that, we introduced a number of innovative polymer technologies serving heat network systems. Sorry, there we go, got the right one. So really our process has been a process of innovation, and we've always looked to see how we can evolve pre-insulated pipe systems to really look for alternatives to carbon steel pipes, and that's one to be able to meet the strengths that carbon steel can offer, or perhaps even build on that, but also to look at the inherent weaknesses of carbon steel, but not just to sort of knock carbon steel, also to see how we can complement carbon steel in our networks. So, for example, if we look at some of the basics, we know that certainly carbon steel has a significant strength in terms of its capability to handle higher temperature in networks. And so over the years, we've developed a number of polymer and composite polymer solutions that will able to sort of close that gap and complement the steel also. And then, of course, there's weaknesses in carbon steel. It corrodes, it rusts, which is unlike polymer solutions that can remain corrosion-free and clean throughout the life of the system, ensuring that the network efficiencies are not compromised and obviously minimising risk of failure. Many other factors that we can consider when we look at this, but all of these have led over the last sort of 20 years in CPV to the evolution of a number of alternative solutions that will either replace or complement carbon steel. So CPV now has arguably the most comprehensive portfolio of pre-insulated pipework solutions. We started initially, as I said, in the 1980s. We were pre-insulating carbon steel pipes, copper pipes. That evolved. We introduced polymer technologies for heating and cooling networks. We added to that with flexible polymer solutions, and then also again with flexible metallic and stainless steel solutions for that. Before moving through to things like thermoset materials and composite polymer solutions that really would sort of close that gap on meeting the higher temperatures that were demanded by heat networks at the time, and then introducing off-site fabrication services to support heat networks. So really now what is the next stage of evolution, or more specifically, what does it mean for heat distribution networks? And how do we sort of move forward this drive towards decarbonisation? So with networks changing, or more importantly, heat, energy sources changing, that has an impact on the networks themselves, and they need to change. And I think fundamentally what it means is we're seeing a significant reduction in temperatures. Clearly, as we have third generation, is now transitioning fourth generation, and as we move towards fifth generation and ambient loop, these temperature networks are lowering significantly. So this means through this process of evolution and innovation of our systems, and how we support it, we need to reset the parameters in terms of when we focus on development of our systems. But I think importantly as well, we also need to look at what are our headline objectives. And this is really to be able to offer a solution that's more sustainable. It's obviously, of course, of the highest environmental credentials, it's high performance, but important as well, we need to look at solutions that will reduce network costs from an installation point of view, and also from an operational cost. So CPV's next stage of evolution is our Hiline Clover system. This is a system that offers a full network solution with a range of products from a DN20 to DN600mm sizes. It's designed to have an operational service life of up to 50 years and capable of operating continuous at 80 degrees C. So indeed it's well placed to deal with certainly fourth generation networks and beyond. Clearly you can see it looks identifiably and distinctly very different to the industry norms. It's grey in colour and it has permanent identification stripes, so it looks very different. It comprises of a high performance polymer service pipe that's capable of meeting performance and service life criteria as demanded by networks and relevant international standards. It's polyurethane foam fill insulation, and it also has a external casing, the grey casing, which is a higher strength polymer casing than you would normally see as an industry norm. So it's well placed to resist the rigours of a long service life below ground. Particularly of interesting and unique as well is our twin pipe system, or the Hiline Clover Duo pipe, which utilises an oval, or I'm often corrected, is actually a stadium shaped casing pipe. So this shape allows for optimisation of thermal insulation whilst offering some material savings. So lots of savings there in terms of transportation savings, and we're offering the Duo system from DN20 to DN100 sizes currently. Also within the range we offer Clover Ambient, so really is an uninsulated pipe, so this is well placed for sort of fifth generation and ambient loop networks. Hiline Clover pipes, they're all jointed with proven fusion welding technology, so we supply all the pipes and fittings assemblies as you would normally expect to see from a pre-insulated carbon steel configuration with spigot ended pipes, and they can all be jointed with conventional and proven butt welding and electrofusion technology. Or alternatively, we have our click weld system as illustrated in the video, and this is quite a unique system where the factory fitted ends are locked and welded on site for a simple electrofusion process. So this again reduces a lot of on-site joints, times and risks associated with this. And this is all really built around the need to address the skill shortage that currently challenges the district heating market, and make this much quicker, easier and risk-free system to install. So we will look at the environmental credentials, Hiline Clover. And perhaps one of the most significant when we make the comparison against carbon steel is the combined CO2 emissions, and that's in terms of the raw material itself and the polymer pipe production. It's well documented that they can be at least half I would say, and probably nearer to the third of that of a carbon steel pipe. This situation is of course further improved when you consider that most carbon steel pipes have been brought into the UK from mainland Europe. All of the CPV's Hiline Clover pipes are manufactured here in the UK, so that has a significant impact on their environmental credentials, and also any waste material that might be generated in the production process is 100% reprocessed and repurposed in-house for our production. We look at transportation resulting for CO2, whilst greatly variable, it's of course significant. Carbon steel pipes can weigh up to 6 times more than a polymer pipe. And as I mentioned earlier, most of that is coming in from mainland Europe. So we can fairly easily demonstrate potential carbon saving from manufacturing the UK of perhaps tenfold that with Hiline Clover pipe over a carbon steel pipe. And then when we look at the Clover Duo with that configuration with a stadium casing, we're clearly shipping far less fresh air around the country on trailers. So if we look at the overall thermal efficiency, the all-important thermal efficiency, we use a water-blown PUR foam, environmentally foam. We achieve a lambda value of 0.021, and generally we have a default thickness that would align with what we would know Series 2 with an EN253. But we can offer alternative series of insulation as and when that's required. So when we compare that to a carbon steel or a typical carbon steel pipe, I should say, we can see some significant savings in cost and reduction in heat loss. And again, as I mentioned, the Clover pipe with its stadium casing, that has the ability to reduce that material content and cost without compromising thermal efficiency. So Hiline Clover pipes and polymer pipes in general, they can offer a number of benefits over carbon steel pipes, but notably, and one that's well understood, is that unlike steel, they won't corrode, they won't rust, and therefore they're not at risk of premature failure to corrosion, and we don't see a reduction in flow characteristics over the life of the system. And this means there's opportunities to save on the overall operating cost, reducing network maintenance, and obviously reducing risk of premature failures. So if we put some of these into an example and we look at how some of these costs and environmental savings stack up. If we took a relatively small scheme, so we said, let's say 1,000 metres of flow and return in a DN200 with a number of branches off at DN80, about 400 metres worth, and we compare a traditional pre-insulated carbon steel network against Hiline Clover, if we rolled all the material costs, the transportation costs, the civils, the pipe install it together, then we can see some savings on the Clover pipe of around about 7 to 8%. If we put the Duo pipe, the Clover Duo, into that equation as well, we can get the savings down to somewhere near about 16% saving. When we look at the reduction in heat loss and the cost associated with that, that's significant as well. We can see a saving somewhere around of about 30%, and again far more again when we start to look at the Duo pipe configuration. And on the basis of the exercise, well, we've considered that we're just simply transporting pipes around the UK. Again, if we bring the factory in there, having to bring steel pipes in from continental Europe, then those numbers really are sort of very conservative indeed. And of course, we have the CO2, the environmental impact. Again, that flows through, and in there is sort of equally interesting numbers in terms of the potential savings. So the Hiline Clover system, as with all of the other Hiline pre-insulated pipe solutions we offer off-site fabrication service. That's growing significantly at the moment. We offer full design support, BIM Revit capability, training at CPV and on-site to support contractors. We also offer the full surveillance system with detect and locate capability on all of the systems as well. Additionally, just supporting that range as a last item there, we're now introducing as part of all of our Hiline ranges the option of Carbo Seal, which in fact is the industry's first dedicated relining solution for networks. And this supports all of the CPV's Hiline pre-insulated piping systems. That brings me to a close. Thank you all for your interest and time. We are exhibiting on the UK Pavilion. So if you want to come along, ask questions, any interest, we'd be pleased to follow up on that. Thank you.
Thanks very much indeed. I think we've got time for about 2 or 3 minutes of questions. So if the gentlemen would like to take their seats in the hot seat, so to speak, we'll see whether we've got any questions from the audience. So are there any questions from any of the audience in terms of the presentations we've seen today? First one being on chemical-free water treatment, second one being on a secondary network loss heat calculator, and the third one being on the new form of pre-insulated pipe. We seem to have shocked and stunned the audience into quiet. So I think the best thing for me is to ask each of the speakers a question in turn. If they pass this microphone along, it's most probably easiest. What do you think is the most exciting development in the network sector, heat network sector, you expect to see over the next 30 years coming along? What do you see as the transformational change? Is it technology? Is it some kind of development? Is it growth? What do you see? What are you excited about?
I won't be here for 30 years, so the industry. I've been in the district heating industry since 2004, and a lot of it in the early days was like the Wild West. There's some shocking systems out there that are on their knees already, and some of them on their knees after a couple of years. So it's exciting to be part of UK DEA with and government stuff happening to tidy the industry up, get it working properly, get it working efficiently, making sure people haven't got horrendous bills because it's costing so much to run. So yeah, there's a lot of stuff to do, a lot of work, and there's a lot of corrective work to do, which people like Fair Heat, for example, are going around tidying up old networks and stuff. So yeah, a lot of, the industry needs some young blood and needs some people, good engineers. That's what it needs.
Thanks very much indeed, David. So new blood and tidying up the industry to make it work. So Mark, can I ask you what you're excited about?
Tough question, really. I suppose from my point of view, looking at the sort of secondary networks and things like that, it's really, I kind of feel for the first time in the last 8 years, people working on these projects when looking at installation actually care. They actually care how the network performs. They actually care what losses they're getting. People are measuring it. And it's all being driven by district heating because people are actually concerned of what the losses they're losing over the system. There's a lot less of, we're just specifying to whatever the minimum is if we want the minimum. It's a lot more, no, we need this level of performance. How do we get it? And there's a lot more engagement coming from designers at all levels because no one's really looked at it in that much detail before. And it's actually quite exciting getting into these conversations with people. Is, okay, how do we drive this forward? It's not just how do we meet the minimums? It's, no, we want to go beyond this. We want to get to this level. How do we do it? And it's actually nice to be challenged as a manufacturer on that point. But it's just generally good for the industry that people are looking at this in detail and actually getting to grips with the whole net carbon zero message. Is how, yes, we need to get there, but how are we getting there and people are actually looking at it? So it's quite refreshing from my point of view.
No, thanks very much indeed. I mean, frankly, I'm excited that Kingspan invested the time and energy to produce his calculator. There was a dearth of knowledge out there in the sector about how to calculate secondary network losses. Just a little fact and figure, if you went for the SIBSI one, you'd still end up with about 35% of heat losses for a typical normal new build property. So you need to be aiming much, much lower than the SIBSI code of practice. Because typically a new build 2-bedroom property built in London will only take about 3,300 kilowatt hours of heat. It's largely actually a process load these days. This is not well known by many people. About 60% of the heat taken in that new build property is actually for domestic hot water, not for heating. The space heating load is only about 40%. So we need to drive those secondary network losses down. And frankly, I'm excited that somebody's invested the time and energy to create a calculator. I'm excited that people are engaging with it. So without further ado, I'll pass you on to Mark to tell you what he's excited about.
I think I just want to carry on really on the theme of my presentation. In fact, there's been a lot of talk within the industry about technology development and innovation when we talk about heat sources and energy sources and the design of systems. But really a forgotten area is the pipe distribution, and it is fundamentally important. And a lot of the technologies that are just being still specified by default, they're decades old, and we've tweaked and messed around the edges of them, but it's really important. You know, it's the lifeblood of these systems. And we've got to innovate, we've got to drive, and we need to be able to support that here in the UK as well. Because as I said, we've got some huge targets that need to be achieved. Let's focus on it and just not forget what's beneath the ground, and that gets the heat from A to B, as it were.
Brilliant. Thanks very much indeed, Mark. I think we've pretty much drawn to a close. I will just mention 3 words, though. Heat network zoning. If you haven't heard about heat network zoning before, come and talk to us over on the UKDA Pavilion, because you should have, because in 2025 the government is setting out zoning for all local authorities in the UK, and it will mean that a particular area in every local authority will be zoned, and you will be mandated to connect to a heat network in that local authority area. So if you have not heard those three words before, you don't know what they mean, you need to find out quickly if you're in the heat network sector or even in the building sector. So come and chat to us or the Department of Energy Security and Net Zero over on our UKDA Pavilion. Without further ado, I'd like you to ask you to put your hands together to give some appreciation to our speakers this morning. Thanks very much indeed.